Let's get some extra practice with calculating a Riemann sum. The first thing that we'll do is look at the statement of the problem and set it up. The problem that we want to tackle is this. We want to use a right Riemann sum to compute the following integral. The integral from 1 to 3 of -2 times x squared plus 5 dx. All right, so we could look at a graph of this function and try to figure out, what kind of answer we should be getting, looking at the signed area under the curve. But I think we'll just go ahead and tackle this one with algebra. You can pause the video if you like and look at a graph of the function. So I want to use a right Riemann sum because that's what the problem is asking me to do. And so what I want to do is I want to cut my interval into n equally sized pieces. And I want to use the right-hand endpoint as my sample point. This is what taking a right Riemann sum means. Okay, so if I look at the interval from 1 to 3, I want to chop this up into n different subintervals, like so. And each one of them, so the whole interval, has length 3 minus 1, or 2. And so if I take n subintervals, each has width 2 over n. 2 is the length of the whole thing, and then I'm chopping this up into n individual little pieces. So the width of this little piece is 2 over n. The width of this piece is 2 over n, etc., 2 over n. Okay, so the next thing that I want to ask is, how do I figure out what these points are? Well, here I start at 1 and I move over by 2 over n, so this is 1 plus 2 over n. And then I move over 2 over n more, so this one is really 1 plus 4 over n, which is really like 1 plus 2 times 2 over n. The next one, sort of running out of space, would be 1 plus 6 over n, which is the same thing as 1 plus 3 times 2 over n, right? Because each time I move over, I'm moving over 2 over n, so I add on another copy of 2 over n to what I'm doing. So the ith subinterval has right endpoint 1 plus I times 2 over n. Okay? Because I've moved over I times by this 2 over n, and I started at 1. So 1 plus I times 2 over n. Right? Hopefully you can see how this might work in general. If I was starting at some other point than 1, I would have that point here, and then however long my subintervals are is what goes here. And I move over one of those subintervals each time. All right. So now I want to write down my Riemann sum. So we know that the Riemann sum is given by the limit as n approaches infinity, the sum from I equals 1 to n, f at my sample point, so xi star, times the length of my subinterval, which is xi minus xi minus 1. Right? So this is evaluate at the sample point, and this is the length of my subinterval. So the length of my subintervals, in this case, we saw just a second ago, was always 2 over n. So this thing is always going to be 2 over n. My sample point is always the right-hand endpoint, in this case. And so we decided that the right-hand endpoints were this 1 plus I over 2n. So here, this is going to be f of 1 plus, we'll write it 2i over n, like so. All right, so I have figured out what I want to do. The Riemann sum actually is just the summation part here, and then I'm going to take a limit over as n goes to infinity to figure out what the value of the integral is, right? We take the limit because we're considering all different partitions, and we know this function is integrable because it is continuous, right? So where's the function f? Well, it's sitting here in the problem. So this is my function f of x. And so what I really have here is the limit as n approaches infinity, the sum from I equals 1 to n. I have f of 1 plus 2i over n, and we just said that f of x is equal to negative 2x squared plus 5. So this would be negative 2 times my x, which is this thing, 1 plus 2i over n squared plus 5. And this is all being multiplied by the length of my subinterval, which is 2 over n. So this is the thing that I want to compute. The middle step in any problem about Riemann sums is always to do a lot of algebra. Make sure you do these steps very carefully. So now we set out to just do a whole bunch of algebra, right? And as we have stated a bunch of times, you want to do this as carefully as you possibly can. So the first thing that I probably want to do is expand out this 1 plus 2i over n squared. So this is going to be the limit as n approaches infinity, sum from I equals 1 to n. I have minus 2. And I either use the formula for squaring this thing, or I put two copies next to each other and use the FOIL method. So I get 1 plus 4i over n plus 4i squared over n squared. Then I have plus 5 and times 2 over n. Okay, so the next step then is to distribute this minus 2. So I get the limit as n approaches infinity, sum from I equals 1 to n. So now I have negative 2 plus negative 8i over n plus negative 8i squared over n squared, right? Distributing this negative 2 plus 5 all times 2 over n. All right, so now I probably want to combine negative 2 and plus 5, so I get the limit as n approaches infinity, the sum from I equals 1 to n. So negative 2 plus 5 is 3, and then I have minus 8i over n minus 8i squared over n squared, and this is all being multiplied by 2 over n. So let's distribute the 2 over n. So I get limit as n approaches infinity, sum from I equals 1 to n. I have 3 times 2 over n, that's 6 over n. I have negative 8i over n times 2, that's minus 16i over n squared. And then the last term, I multiply by 2 over n, I get negative 16i squared over n cubed. Okay, so this is looking pretty good, and I feel better about actually being able to do the sum in this case. So I have now, using some of my rules for sums, limit as n goes to infinity. Here the 6 is a constant, so I can factor it out. I have 6 times the sum I equals 1 to n of 1 over n, which is also still a constant, so we'll pull that out in a second. We also know that the sum of terms is the sum of the terms, so we can split the sum across all these different terms. Here I'll factor out the 16, which is constant, as well as the n squared, which is constant. Forgot to do that in this step, but we'll get to it in a second. So 16 over n squared doesn't have anything to do with the I, which is what's changing in the sum here, so I can factor that out. 16 over n squared times the sum from I equals 1 to n of just I. And then in the last one, the 16 over n cubed is constant, doesn't have anything to do with the I, which is changing. And I have the sum from I equals 1 to n of I squared, right? So we'll throw another step in here to pull out this 1 over n. So this time I have 6 over n, and the thing that's left in the sum that I'm adding up is just a 1. Because if I multiply this back together, I have to end up with the 6 over n that I started with, right? So then I have minus 16 over n squared times the sum from I equals 1 to n of I, and 16 over n cubed times the sum from I equals 1 to n of I squared. And the good news is that this sum I have a formula for, this sum I have a formula for, and this sum I also have a formula for. Okay, so when you're doing these Riemann sum problems, you should end up eventually, at least if we're asking you to do a lot of calculation, you should end up with some sums that you already know how to evaluate. All right, let's keep going. So now I know that the sum from I equals 1 to n of just 1, well, that's 1 plus 1 plus 1 n times, so that's just n. So I get the limit as n approaches infinity, 6 over n times n, which is this sum. I have minus 16 over n squared, my constant. Well, the sum from I equals 1 to n of I, we said, was n times n plus 1 over 2. And I have then 16 over n cubed is my constant term. And this last sum, we said, was equal to n times n plus 1 times 2n plus 1 all over 6. Okay, back to algebra again. Here I have an n in the numerator. Here I have an n in the denominator. So those guys are going to cancel. Here I want to expand, and here I want to expand. So I did some of the algebra earlier, so you'll have to check and make sure that you get the same thing as me. So I get the limit as n goes to infinity of 6, these n's cancel, minus 16 over n squared times, here I have n squared plus n over 2. And then here I have minus 16 over n cubed, and when I expanded this one out, I got 2n cubed plus 3n squared plus n all over 6. Okay, so just a little more algebra to make this look a little cleaner. I have 6 minus, let's rearrange this term so that I have the constants on the front and then just variables. So I have 16 over 2 times n squared plus n over n squared. That all multiplies together to be the same thing. And then here I have 16 over 6 times 2n cubed plus 3n squared plus n all over n cubed. Right? Now I have done all the algebra that I need to do to make the limit really easy to take. Finally, let's take the limit and see the answer to our question. So let's go ahead and take this limit. The first one, so I remember that the limit of the sum is the sum of the limit, so I can take each of these limits individually. Also, this limit and this limit are limits that we've been doing about since week 2, right? And we've talked about a couple of different ways to approach these. So I'll just tell you what the limit is and leave you to calculate the actual limit by yourself as some maybe more practice for possibly the final exam. So calculate these limits, make sure you get the same thing as me. So I got limit as n goes to infinity of this, now I'm taking the limit, so I don't need that. All right, limit as n goes to infinity of 6 is just 6. Here I have a constant, 16 over 2, and I take the limit of this term, the first green box, and since it's kind of n squared over n squared, the limit is 1. Finally, I have this coefficient 16 over 6, and here I have 2n cubed over n cubed, so the limit is going to be 2. So then, all I have left to do is simplify this number. I actually put it in my calculator to figure out what I got, and the answer is negative 22 over 3. So the total amount of signed area under the curve, negative 2x squared plus 5, between 1 and 3, is negative 22 over 3. If you look at a graph of this function, that should make a lot of sense. Most of the area is below the x-axis, so we were expecting to get a negative answer. This process should hopefully help you with some of the problems on Mooculus this week, as well as some of the problems on the quiz. Riemann sums are pretty important, but really tedious. That's why next week, with the fundamental theorem of calculus, we'll learn how to work around these a little bit. Again, remember that the most important thing when it comes to doing Riemann sums is to do all your steps very carefully and make sure you're going nice and slowly with the algebra so that you don't make as many algebra mistakes. Good luck, and let us know if you have any questions.